Hello everyone. This study is the result of my degree thesis supervised by Professor Sergio Pone and discussed in 2019 with subsequent addition until 2020. It proposes a new construction system made of double-frame cross panels to be used for the design and construction of freeform architectural structures. The aim of this study is to combine geometric, productive and constructive aspects with form-finding processes, keeping their self-compatibility with the designer's intentions. It comprises three main phases: the design of the construction system through the identification of the elements, their interlocking methodology and the construction constraints, the creation of the parametric tool to fit the construction system to a given freeform, and the implementation with digital fabrication through the transposition of a digital parameterized model into a buildable prototype. So, in cross-panel system, each panel has half-wood notches in which a dowel that is exactly half the thickness of the joint is removed on both pieces. In this way, the contact surface is equally distributed between them. The mutuality ratio that is created ensures that the cross-panel system is characterized by the absence of hierarchy among the components. In fact, each panel is both a connecting element and a node, as you can see in this example. The possible variations within the cross-panel system are determined by two characteristics: the panel shape, that has formal nature and modifies the aggregation pattern among the panels, and the notch's angular rotation, that involves moving the joint from a perpendicular position to the panel perimeter to a variable one. Therefore, assuming a system formed by square panels, it is possible to identify two joint directions. By varying the notch angle in only one direction, the elements can be used to create archival systems. If the angle is varied in both directions instead, the possible configuration multiply, and the system can be applied to discretized freeforms. However, the Albert joint does not ensure a solid and robust connection. This is due to the small contact surface among the panels. This causes the joint to be subject to twisting moments along the notch's axis. The system is thus weak and subject to cracks. To solve this, it has been necessary to design a reinforced version of the joint by doubling the panels in both interlocking directions, increasing the contact surface and the torsional strength and the stability of the components. This solution also avoids the use of glues and screws, thus making the system reversible. The second problem I dealt with was about fabrication and constructability. In fact, 3-axis laser cutting machines allow only perpendicular cuts to the working surface. Furthermore, joints with multiple degrees of freedom would have prevented the simultaneous sliding of several components during the assembly. For this reason, the orthogonality condition between the normals of each pair of panels was essential for the correct functioning of the system, identifying through experimentation with 1 to 2 scale elements an acceptable range within which the condition can be satisfied, between 80 degree and 92 degree. In detail, only the XY angle must comply with this condition. The XZ and YZ angles can vary, allowing the correct fitting of the elements to the surface. In the next phase, computational design strategies have been developed in order to study the adaptive capabilities of the system. It was done in Grasshopper by creating a parametric definition that allows the fitting of the construction system on a given freeform. The definition has been divided into three parts: the first frame, with panels whose normals are perpendicular to the surface, the second frame with panels whose normals are rotated by 90 degrees in the U and V directions of the surface, and the nesting and labeling phase, where notches and cutting patterns are created for the digital manufacturing process. Once completed, the tool has been tested to reproduce other architectures by replacing their structural system within the cross-panel system, like the Serpentine Gallery by Alvaro Siza and the Smithsonian Courtyard by Forster and Partners. The system has been further tested through a digital fabrication process. For this purpose, a temporary wooden pavilion has been designed to build a 1:10 scale model. The prototype was produced using a 3-axis laser cutting machine. The cut was preceded by a pre-production phase consisting of nesting and labeling made with OpenNest, a Grasshopper add-on capable of unrolling, packing and numbering the elements. In 2020, the research saw new additions aimed at refining the parametric tool. The goal was to simplify the construction of the elements on the surfaces and to ensure that orthogonality condition was perfectly respected. The new version of the tool integrates two raster add-ons, Lunchbox and Kangaroo. The first one is capable of discretizing surfaces with a wide range of panel shapes, while the second one is a live physics engine used to improve the panel planarization. The second optimized element has been the joint angle between the panels of the first and second frame. In fact, with very regular surfaces, the orthogonality condition would not be satisfied in all the joints, preventing the correct assembly of the panels. To overcome this, a geometric theorem has been applied to each pair of the first frame panels, stating that if a straight line is perpendicular to a plane, every plane passed through this line is perpendicular to the plane itself. In this way, wherever the shape of the surface is, the first and second frame panels will always be orthogonal to each other. The panels of the second frame were subsequently oriented by detecting the mean vector between each pair of the panels of the first frame, that is the resultant of the sum of normals belonging to both planes. The structural framework that is determined with the new optimization is therefore slightly different from the previous one, since the elements of the second frame are now perpendicular to the edges shared by each pair of contiguous panels. Further studies and optimizations are needed, aimed at parametrizing the sides of the panels of the second frame more precisely. Meanwhile, the results achieved shows that DCPS represents a valid alternative for the design and construction of freeform architectures, dynamically responding to the changes of the base surface. Thank you for your attention.